Okay, so as we've seen a couple different times, it's not always super convenient to find the area between two curves vertically. Okay, yesterday we had a sideways parabola and a line. You remember that? And we had to split it into two integrals and do the calculations for this integral and do the calculations for this integral and add them together. Same thing happened up here on number 21. Okay. Well, what if we had another option? Okay. Look at this picture right here. If I asked you to find the area between these two curves, doing it vertically would be a nightmare. Okay. But if we can write our equations in terms of y, so now they're functions in terms, well, they're not functions, but they're in terms of y, we can use our same area concept with rectangles that are horizontal and have thickness dy. So now instead of vertical rectangles and we're taking the integral of top minus bottom dx, now what we can do, or what we have the option of doing, is we can take the integral of right minus left function dy. Top minus bottom dx, or now we have right minus left dy. So we're actually going to go back to one of our examples from yesterday. That one with x equals y squared and y equals x minus 2. We're going to go back to that example and look how we can do that with one integral instead of two. So I'm going to go ahead and have you write down our equations again and redraw the picture. Okay? We'll work together on the integral, but at least for now, write down your equations and redraw the picture in this set of notes. Okay, and yesterday we did some algebra. What was the coordinate of this intersection right here? 1, -1. And the coordinate of this intersection right here? Okay, so now what we can do, instead of drawing a horizontal rectangle where our bottom function switches, we can draw a horizontal rectangle with thickness dy. Bless you. Okay. This rectangle has thickness dy. So that's what tips us off, okay, my integral is going to be in terms of y. Okay? But what's nice about it is our equation is consistent all the way on the right, and our equation is consistent on the left. Okay? This blue equation that I'm highlighting right here, that's x equals y squared. And then this red equation right here would be x equals y plus 2. So, right minus left, we're going to write in here y plus 2 minus y squared. And now our limits of integration are going to have to match our variable. So since we're doing dy, we're going to go from -1 to 2. Your limits of integration are your y intersections. We have dy, and inside we have, in terms of y, our equations right minus left. Okay, so now I only have one integral to do instead of 2. Math 9, this in your calculator. Tell me what you get. Hopefully it's the same as what we got yesterday, huh? So I would just type it into your calculator using your X button, because it's just your calculator doesn't care what you're setting up. So still use the X button, it just will save you some time. Max, what do you get?
I have 4.5.
4.5. This is what we got yesterday, isn't it? Okay. Now, if we had to do this with a calculator, I don't know if setting up 2 integrals is really that much more work than setting up 1. But if this was a non-calculator problem and you had to do the integration by hand and you had to do the fundamental theorem of calculus of f of b minus f of a 2 times instead of 1, this is definitely going to be a time saver. Okay. There's also going to be times where we literally cannot use x's. Okay, here we could use x's or y's, but there are going to be situations where y is our only option.
So yesterday we got like 4.5 and then a bunch of guesses. Does that mean anything?
Okay, so yesterday we got like 4.500000002 or something like that, right? So your calculators, as sophisticated as they are still approximating. So technically the answer is 4.5, 9 halves, whatever. But every once in a while your calculator will have just, I don't want to say trouble, but it's approximating, and so it might give you like lots of zeros and 1 or a 2 like it did yesterday. Really that just means 4.5. Yeah. So we'll see that especially in this chapter, what I'm asking you to use Math 9 quite a bit. Your calculator's approximating, so we can do a little bit of assuming with, okay, if it's 4.5000002, okay, we'll just call that 4.5. We'll call it 9 halves. Okay. All right, I want to make sure that we can come up with these graphs. Okay. It's been a while since you've really had to graph horizontally opening parabolas, so write these down and then we need to remember how to get these graphs. Okay, so let's start with negative y squared plus 10. Which way is that parabola going to be opening? Left. And that plus 10 is shifting it which direction?
Right, up, down.
Right. It's going to be shifting it right. So if that were a y equals negative x squared plus 10, it would be opening down, shifted up. So now we just need to change that to right and left instead of up and down. Okay, since the x and y are in different places, we have to just kind of like switch up, down, right, and left. So this is going to be opening to the left, shifted 10 to the right. Really don't like that parabola, but I'm not going to redraw. Make yours better than mine. Okay. Y minus 2, the quantity squared. Which way is it going to open?
Right.
To the right. And that 2 is shifting it up 2. So here's our region. Okay. Technically, yeah, it would be possible to write these in terms of x, but we would have to, if we used vertical rectangles with thickness dx, how many different integrals would we have to set up? 3. Top function changes here, bottom function changes here, so we'd have 3 different intervals. Okay, not pretty. But if we use horizontal rectangles with thickness dy, then all we have to do is worry about right function minus left function. Ooh, but what do we need? We need our limits of integration. We need these intersection points right there. Okay? We need to know when negative y squared plus 10 is going to equal y squared minus 4y plus 4. I don't know how much guessing and checking is going to be efficient here. Okay. So if I move everything over to the right side, we would have 2y squared minus 4y minus 6. So y squared minus 2y minus 3. All right, what does that factor to?
3 and negative 1. Y minus 3.
So that 3 and negative 1 are our intersection points that we would use for our limits of integration. All right, math 9, that bad boy. What do we get? 16/4. And if it's possible to turn it into a fraction, I like fractions. You got what? You got 40?
I got 64.
But they're negative twice to start with. So you can roll negative. Okay, so really, it's the same thing as yesterday, right? We're just going right minus left instead of top minus bottom. We're using y's instead of x's. Okay. Now we have about 20 minutes left in class. I probably will give you some time to start your homework, just to keep this Friday party going for you, Max. Okay. But I do want to do one problem that is going to be make you think outside the box a little bit. So write down what you need to and start thinking about it. Maybe draw a picture. And we'll set it up and work through it together. Okay, so here's our region. It goes up to y equals 4, correct? Okay. So I want some horizontal line, y equals b, to cut this exactly in half. What? What's the matter? All right, so how are we going to figure out where that is? Okay, you said, what did you say? Okay. Okay, so you're saying find the area and cut it in half. Mm-hmm. Is that what you were saying?
Yeah, I was saying that find out half the area is and like
Okay. So let's find the whole area. Did you have a suggestion? Yeah, we'll definitely have to set up an antiderivative with B. Yes, for our area. So let's work on what the whole area is. Okay? How would you like to do that? Using X or using Y? Okay. Yeah, because you could call this X equals radical Y, and this guy X equals negative radical Y. Those would be your two equations if you wanted to use Y's. Okay, which we'll need to here. If we're talking about the whole blue area, then if you wanted to use dx's, your integral would be from where to where? -2 to 2 of 4 minus x squared. Okay, a little nervous. So you reassure me that we got it. We got it set up right. So if we find that area, I'll let you math 9 this one. What is it? 32 thirds. Better double check Ethan. Yep. Double check, triple check, quadruple check. We're getting 32 thirds. Okay, so what is half of 32 thirds? 32/6 or 16 thirds. So half of our area, 16 thirds, needs to equal the integral from, now we're going to have to use b. Okay, we're going to have to use b. So we can do this a couple different ways. Okay, let's use it as our limit of integration. We could go from 0 to b of right function minus left function dy. How do you feel about that setup? Okay, so from 0 to b, that's the half, right, of right minus left. So now, math 9 is not going to help us here. We have the integral from 0 to b of, that really is just 2 radical y dy, isn't it? Okay, so 2 radical y, that antiderivative, we get y to the 3 halves times 2 thirds. So now using the fundamental theorem of calculus, we know that that integral is 4 thirds b to the 3 halves minus 4 thirds 0 to the 3 halves. Don't think that's necessary. When we take 16 thirds divided by 4 thirds, what do we get? So we have b to the 3 halves equals 4. So to get b by itself, we would have to take each side to the 2 thirds power. And you can just leave it as 4 to the 2 thirds. It's not going to be a nice number. But that would be exactly what would cut it in half. Okay, that's probably not the last time you're going to see a problem similar to that. So I wanted to at least do one together before we started talking about volume next week, to where I might give you a problem like this again with volume. So we have about 11 minutes, maybe 12 minutes left in class. What I'd like you to do is go ahead and start your homework. Get maybe 2, 3 problems done before you leave for the weekend. It looks like, once again, I have problems that I need you to set up and integrate by hand. So number 26 and 27 are labeled as no calculator for you setting it up, integrating it, all of it. I need you to still practice your integration skills. So every homework assignment, I'm going to give you 2 or 3 problems to do all the way by hand. The other ones, I still want you to set up without a calculator unless it says to use a calculator. And then Math 9 would be the only function you're really using your calculator for. But let's start our homework.